All right, this is part 2 of 12-tone music. So we're going to go over invariant, symmetry, and combinatoriality. See that 5 times fast. All right, invariance. We've talked about invariance before. It basically means like a common tone or something's in common, right? So invariance means that some aspect of a row is preserved if you transpose it or invert it, okay? So something that will always be preserved is the intervals, right? So the adjacency interval series, if you remember that shows us the intervals between each pitch class, that will be the same in every transposition. Okay. We can also see invariance in like subsets of the row. So if you think back to the last video, we saw that in like, for instance, the Webern that we looked at. So there were like pitch class sets within it that were actually the same in like subsets in the row. Okay. All right, if you look off to the side, you can see some more invariants. Okay, so the first one comes from Schönberg's Klavierstück, which just means piece for piano. Okay, so if you look at the tetrachords at the first of the prime version, so the C, G, D, D flat, if you look at in version 2, we actually have the same notes, not in the same order though, right? But those were like kept in common, right? So if you use it as a tetrachord, it would look the same, basically. Okay. Because you don't have to use these as just melodies, right? You can use these for harmony too. You can use them to build your harmonic structures as well as melodic structures as well. Okay. All right, and then you can see in the lower one, we have trichords instead, right? So we have 3 notes that kind of map onto each other in version 5. So the one that's been inverted, but also up 5 semitones from the original inversion. Okay. These examples are going to use the integers for the notes, for the names of the notes, just for ease. Okay. Okay. So you can see that last one, there's an example now. So this is the Schoenberg, that was that last one. The last example, because this is the string quartet number 4. Okay. So you can see the first, well, the top part is a prime form of the row. Okay, so it's prime 2, so that means it's been transposed up 2 semitones. Okay, the one on the bottom is inversion 7. Okay, so it's an inversion format of the row, but it's also transposed 7 semitones away from the original inversion. Okay, all right, now if you look at this, there's some invariance with it. Okay, so 912 and 780 are like the integer numbers for the pitch classes. Okay, and then right here they're just swapped, right? So this like trichord basically is swapped right here. So 912 down here, and then right here the 780 swapped up here, and then it basically shows the same invariance over here too. Okay. So it just gets, variance basically means it's even more complicated, very much more mathematical. Okay, we saw some symmetrical rows in the last video as well. So symmetrical rows can be read forwards or backwards, and the intervals will all be the same. Okay, combinatoriality now. So a combinatorial row is built from like hexachords. Okay, so you have to think of the row in like 2 halves basically. So there's 6 pitches in each half of the row. Okay, so combinatorial rows means that the first 6 pitches of the original row and the first hexachord of a transformed row can be joined together. So it's like complements basically to get all 12 pitch classes. Okay, so a way to think of this is hexachordal combinatoriality. Okay, so we have 2 hexachords that come together. Okay, so types. Okay, so first one is prime combinatoriality. That means that like a different form of the prime row could be just transposed, and then we could combine it with the original prime, so P0, to form an entire row. Okay, so if you look at this one, so basically it's saying, okay, H1 means hexachord 1, we have hexachord 2 right here. If you look right here and compare like the integer numbers for the pitch classes, so prime 0, so 0, 1, 5, 4, 9, 8, right? That's our first hexachord. And then our second hexachord, 7E, E is the B, remember, so we're using T and E for B flat and B. Okay, so ET326. Okay, so if you compare it, hexachord 2 right here is actually the same as hexachord 1 for this prime 6, so the one that's been transposed up a tritone. Okay, it's not the same order, but the same pitches, right? Same pitch class. Okay. Same thing for the second half, right? This is actually the hexachord 1 of the original. Okay. So prime combinatoriality just means that we can use another version of the prime row and use a hexachord from that to combine with the original one, okay, to give us all 12 pitches, all 12 pitch classes. Okay. Okay, next one. So inversional combinatoriality means that we can, so we're still going to combine something with the original prime form of the row, but inversional means we can use an inversion and use a hexachord from an inversion to combine. Okay, so you can see it formatted here. It's kind of the same thing as the last one, but this time we're using an inversion to combine with the original row. Okay. Okay. Next one is showing you retrograde combinatoriality. So that means that we can use some form of the retrograde form of the row to combine with our original prime to give us all 12 pitch classes. Okay. All right, then last one is the retrograde inversional combinatoriality, which is just the same thing as all the other ones, except now we're going to use a hexachord from the retrograde inversion row and combine it with the original prime form of the row to give us all 12 pitch classes. Okay. All right. Okay, and so just a little bit more about serialism now. Okay. Serialism, so we're talking mainly like post 1945 in these ones. Okay. We're going to talk about a couple of composers specifically. So Pierre Boulez, if you're saying it French, but most of the time I hear Pierre Boulez. Anyway, okay, so he used what's called multi-serialism, okay, or also what we sometimes call total serialism. Its other name is integral serialism. They're all the same thing, okay. I like to use total serialism. It just means that we're using some kind of almost formula for everything besides just the pitch classes, okay? So we tend to think of serialism as just 12-tone rows, right? But that's not actually accurate, okay? So total serialism means that we haven't just like ordered the pitch classes, okay? So we haven't just serialized the pitch classes, but we're also going to like order or serialize other things too. Okay, so examples of other things that we can almost like put a formula onto would be durations, right? So like note values, okay, intensities, so dynamics, right? So we can have like kind of a formula for intensities, and then modes of attack, okay? So that would mean like staccato, legato, accents, that kind of stuff, okay? Usually Boulez, especially Boulez, would use what's called multiplication to generate his pitch structures and all of his other kinds of like kind of formula type of things too. So different composers have different ways of coming up with their like patterns basically. So it's basically just saying that it's not just the notes that have a pattern, but it's everything else too. So, I mean, a pattern could also mean that maybe you're going to serialize the durations, so the note values themselves. And maybe your pattern is quarter note, 2/8 notes, 3 16th notes, and then, you know, something else, right? So that means that that pattern would then like pop up all the time, okay? There are other ways, of course, that you can do this too. If that would be a very simple pattern, usually they're more complicated than that. Okay. Milton Babbitt was a mathematician, which probably won't surprise you if you look at his music. So he used total serialism as well, okay, but kind of complicated, very mathematical approach to it, okay. He would use what's called a trichordal array. So he would combine 4 row forms and they would feature hexachordal and trichordal combinatoriality. So what we just looked at, okay. So not just like hexachord combinatoriality, though, you could also use trichord combinatoriality. So that would mean you would have like 4 different trichords, right, that you could combine to make a complete row. Okay. He also used durational rows, so that means that the note values themselves are serialized as well. Okay. And he used time point rows too, which we won't get much into. Okay, but this is just to kind of tell you about how total serialism works, that we can serialize more than just pitch classes, that you could serialize everything basically, if you want to be completely mathematical about it. Okay. All right, that is it for part 2 of the 12-tone method.